AB Calculus, Section 1.4, day number 2, continuation on trigonometric functions and their inverses. The objectives for this video are periodic functions and their properties, some transformations on sine, cosine, and tangent, as well as some inverse trigonometry. So we're going to talk about the period for sine, cosine, and tangent. But before we do, I want to write down some general equations for sine and cosine. Okay, so I could replace sine with cosine, and all of these properties would be the same. So these values a, b, c, and d, these are constant real numbers, and they represent different transformations upon the functions sine or cosine. So the absolute value of a is called the amplitude. That's the vertical stretch or shrink. B is going to be what we call it has an effect on the period of the function. So how often the period happens, or how often the function repeats itself. So with sine and cosine, in order to find the period, we would take 2 pi and divide by b. Okay, C is going to be our phase shift. And a phase shift is a horizontal shift, so it could be left, could be right. And D is our vertical shift. Oops, I spelled shift with a pi at the end. That's cool. Okay, now the only difference between sine and cosine and then tangent, same values would apply to a tangent function. We'd put everything in the same location. Everything is going to be the same. Really, there's no amplitude to tangent, so it's not really applicable. Okay, so amplitude isn't necessarily applicable. It does affect the vertical stretch, shrink, or vertical reflection. Phase shift is exactly the same. Vertical shift, same effect, but period is unique, okay, because the period of tangent is just pi units. It cycles once every pi units instead of 2 pi. So the period for tangent is going to be pi over b. So as you can see, we're answering this question. The period for sine is 2 pi. The period for cosine is 2 pi. But the period for tangent is pi units. And we'll see that graphically in just a minute. Okay, so let's look at example number 1 and sketch this graph. We're going to transform the function y equals sine x. Okay, and we're going to transform it by manipulating it using this value 2. So that value 2 is actually b. So that means we're going to have a transformation on the period length, which means the period, instead of being 2 pi, is now going to be 2 pi divided by 2, which means the period will be pi. So we are shrinking the function horizontally. So let's just graph what sine x normally looks like. So sine x has, we'll graph one period, has a max value at 1 and a min value at -1, and it hits those max values and min values in this orientation. So normally the full period would have been 2 pi, but because now the period is only pi units long, we've cut the length of a period in half. So this will be pi over 2, this will be pi over 4, and this will be 3 pi over 4. So that would be the graph of sine of 2 pi, or excuse me, sine of 2x. Now let's look at example 2. Looks like we're doing a different transformation on cosine. So the 2 here is the value of a. So instead of cosine, which we're not changing the period at all, so the period of cosine will be 2 pi. Instead of changing the period, we're changing the amplitude. So now the max value will be 2, min value will be -2, and of course cosine hits max values at 0 and 2 pi, a min value at pi, and then 0 in between at pi over 2 and at 3 pi over 2. So the graph of 2 cosine of x should look like that. Okay, now let's talk a little bit of inverse. Now sine x, I want to sketch sine x, and I'm going to sketch it for a significant amount of, a significant length, I guess I should say. I'm going to go from negative 2 pi to 2 pi. Okay, so sine would do a little something like this, and get max and min values in between 0 and pi, and then pi and 2 pi. Oh, not well done. Let's try that again. I like that. That's better. Okay. So there's one period of sine, and this isn't to scale, so I might have some issues with how I orient this inverse function, but we'll get it. It'll be all right. Okay, so there's 2 periods of sine. All right, so based on the previous lesson, we talked about the horizontal line test. Well, the function sine x does not pass the horizontal line test. It doesn't, all right? So we have to restrict it, and that's why we're restricting it from negative pi over 2 to pi over 2. So we're going to restrict it simply to this portion of the graph, and the reason why is because now it would pass the horizontal line test so that its inverse, which will be inverse sine of x, will pass the vertical line test. So we can isolate some points here. This right here is the point pi over 2, 1. Of course, this is the point 0, 0. And this is the point negative pi over 2, negative 1. So the inverse would have the same points except their x's and y's flipped. Therefore, and this isn't going to look perfect, but if I had 1 pi over 2, 1 pi over 2, and again, the orientation of how I've sketched this is off, so it's not going to look great. And this would be negative 1, negative pi over 2. The graph should look kind of like that. Now, again, it's not well sketched. What it really should look like is, because pi over 2 is bigger than 1, it should look more like, here would be the graph of sine. And it would look like this. And here would be the graph of inverse sine. It would look like that. So it's not perfect, but it's all good. All right, we're not worried about the sketch of inverse sine. We're worried about how to use it and what its domain and range are. So we restricted the domain of sine to go from negative pi over 2 to pi over 2. And its range, of course, we already know, goes from negative 1 to 1. So the domain on the inverse will go from negative 1 to 1, and the range will go from negative pi over 2 to pi over 2. This is important for us because this range, when we work with a question, for example, like inverse sine of 1/2, well, the sine equals 1/2 in multiple locations, but our answers must be within that range. Okay, so we'll see that in a few minutes with a couple of examples. Let's move on to inverse tangent. Okay, so tangent we sketched in our previous lesson, but we saw that tangent repeats itself every pi units. So this was at x equals negative pi over 2, and we have another horizontal or vertical asymptote, at x equals pi over 2. And then the graph of tangent looks like this, okay, where we've got, it's not perfect, but it's going to work, okay? So at pi over 4, we have an output of 1, and at negative pi over 4, we have an output of negative 1. Okay, so the domain we've restricted. We've said from negative pi over 2 to pi over 2. Okay, so that's going to be equivalent to the range of inverse tangent. So that means we're going to have horizontal asymptotes that are going to be enclosing this function. All right, so what's the range of tangent? Well, we don't have a limit on the range, so all real numbers. Therefore, the domain on inverse tangent will also be all real numbers. So now what will happen for us is we will get horizontal asymptotes at y equals negative pi over 2 and at positive pi over 2. And then the orientation of inverse tangent will end up, this won't be perfect, but it will end up looking like, I'm going to try to make it look pretty good, just like that. Okay, where, let's see, right about here at 1, this would be the output pi over 4. And right here about negative 1, this should be the output negative pi over 4. It's not perfect to scale, but that's what arctangent would look like. So remember this, again, when we're dealing with inverse tangent, we should get outputs between negative pi over 2 and pi over 2. Okay, let's look at inverse cosine. Okay, so the natural restriction that we put on inverse cosine is from 0 to pi. And the reason for that is because it passes the horizontal line test. So here's 1, here's negative 1, here's pi over 2, and we've got, oops, that was poorly done. Just like that. Okay, so here's the point pi comma negative 1. Here's the point 0 comma 1. Here's the point 0 comma pi over 2. Now I may have some issues here with what my next portion of my graph looks like, but we do know that if 0, 1 is on cosine, then 1, 0 should be on inverse cosine. So it should be the point 1, 0. If 0 pi over 2 is on cosine, then pi over 2, 0 should be on inverse. And if pi negative 1 is on cosine, then negative 1 pi, negative 1 and pi. Oh, this is going to be interesting. Let's see if I can get it about accurate. Not quite. Let's try again. This will be interesting to sketch. There's your sketch of inverse cosine. Now, with any one of these, you notice that if I reflect over the line y equals x, I get a nice line of reflection, or a line of symmetry if I were to reflect the two. So there you go, there's inverse cosine. Domain of cosine, we went from 0 to pi. Of course, the range is from negative 1 to 1. Therefore, then for inverse cosine, we would have a domain of negative 1 to 1, but a range of 0 to pi. So here's where your range of possible values for an inverse cosine problem would exist. Okay, let's look at a couple of examples here below. So evaluate inverse sine of 1/2. Okay, inverse sine of 1/2. Well, the sine is positive in first and second quadrant, but because when we deal with inverse sine, the range of inverse sine of x is between negative pi over 2 and pi over 2. So that isolates for us quadrant 1, right? So in quadrant 1, where is the sine 1/2? Since the input is a ratio, the output will be an angle. Okay, the outputs of inverse sine, cosine, and tangent are all angles. So what angle gives us a sine of 1/2? And that would be pi over 6. All right, if I look at this unit circle special right triangle, if this is a 30, then I get a 1/2, and I get a 1 and a root 3 over 2. So I can see that my y value, which is equivalent to the sine, is 1/2. Therefore, pi over 6 is equivalent to 30 degrees, and that's our answer. Okay, inverse cosine. Okay, so the cosine is positive. Where's the cosine positive? Cosine is positive in the first and fourth quadrants. However, the range of inverse cosine is 0 to pi. Therefore, again, this will put me in quadrant 1. Quadrant 4 is out. That's not in that range. So 1 over root 2 should tell you pi over 4 when you're in quadrant 1, and then appropriately scaled as you go from quadrant to quadrant. Okay, let's look at tangent. So where is the tangent positive? Well, tangent is positive in quadrant 1, quadrant 3. However, the range of inverse tangent, as we spoke about, is not inclusive, but from negative pi over 2 to pi over 2. So again, that'll isolate quadrant 1. Where is the tangent 1? Well, the tangent is 1 in an isosceles right triangle where the angles are equal, right? So I would have 1 over root 2, 1 over root 2, and 1. Therefore, these angles, both of them, would be the same. Thus, we would have 45-degree angles, or pi over 4. Okay, let's move on and look at a couple more questions here, and then that'll be good for today's video. Okay, let's work with another inverse tangent question. Again, the range of inverse tangent is from negative pi over 2 to pi over 2. And tangent is negative in quadrants 2 and 4. So we're going to be working in quadrant 4 here. And what I'm going to do is I'm actually going to sketch a triangle that has an opposite side and an adjacent side of negative 1 and root 3. And we'll see what happens here. Quadrant 4. So opposite, negative 1, adjacent, root 3. What would this angle be? Well, this would be a 2. Now it's not something typically that we've seen with regards to unit circle type triangles, but if I divided everything by 2, it would be. So it looks like I would get an angle here of pi over 6. Now that's the reference angle, but because we're dealing with angles between negative pi over 2 and pi over 2, you might think, well, it'd be 11 pi over 6, and that's also not true. Okay, the first one is a reference angle. The second one is the correct location, however, it's not within the range. That range needs to be satisfied, which would be negative pi over 6. Okay, now cosecant. I wouldn't necessarily work with cosecant, secant, cotangent when it comes to this. What I would do is if you have cosecant, inverse cosecant of A, I would rewrite that as sine inverse of 1 over A, right? So I'd just do the reciprocal. So in this case, cosecant inverse of negative 1 is the same as sine inverse of negative 1, right? Because negative 1's reciprocal is still negative 1. So that's quite simple and easy to work with in this case. So where is the sine negative 1? That's what we're being asked. Well, there's only one place where the sine equals negative 1, right? If I look at these are called quadrantals. This is the point 0, 1. This is the point 1, 0. This is the point 0, negative 1. This is the point negative 1, 0. As I look at the sine values, which are all the y values, the only place you'll ever see sine equal to negative 1 is down at this location where theta or x or whatever it might be would equal negative pi over 2. Now you might fool with that and think, well, it's 3 pi over 2 because you're thinking positive angles. But that's not true, okay? So because sine, or inverse sine, this is why it's not true, because the range of inverse sine is from negative pi over 2 to pi over 2. 3 pi over 2 doesn't satisfy that range. Therefore, we have to use negative pi over 2. So the answer to inverse sine of negative 1 is negative pi over 2. All right, outstanding. Let's look at a couple more examples. When you think about finding an angle, right, when you're using inverse, you should think, I like when the ratio is unit circle friendly, right? But this one isn't. This is 2/5. So if the inverse sine, if the sine is 2/5 positive, right, the sine would be positive in these two quadrants. But I'm not going to, again, for the same reasons as before, I'm not going to use quadrant 2 because that's not within the range of inverse sine. So I'm going to sketch this in quadrant 1. So the sine is 2/5. That means 2, 5. So the third side, of course, would be 25 minus 4, square root of that. So square root of 21. I just used unit circle, or excuse me, Pythagorean theorem to do that. So theta is this angle, right? This blue angle. Now, I don't really care what that angle measure is. What I care about finding is the cosine of theta and the tangent of theta within the context of this problem. And I can do that without ever knowing the angle's measure, right? Because I now know, using the Pythagorean theorem, the third side, so I can find the cosine of theta, which would be root 21 over 5, which is adjacent over hypotenuse, and the tangent of theta, which would be 2 over root 21, which can also be written as 2 root 21 over 21. Okay, so whenever you're given a ratio that's not unit circle recognizable, or not something you've seen within the unit circle, this is likely the process you're going to be using. Okay, let's look at example number 7, and that'll be the last one for this video. Okay, so we got a lot going on here. What we've got here is the sine of an angle, which means I just want a ratio. All right, so what is the angle? Well, the angle is the inverse tangent of x. Well, what is that, right? Because I don't have a ratio. Well, you kind of do. Anytime you see a variable involved in an inverse, for example, x in this case, what you want to do is you're going to first isolate to quadrant 1. So always go quadrant 1. And within the ratio, I could imagine that x is equal to x over 1. So the x is my my opposite side, right? Because I'm working with tangent, and the 1 is my adjacent side. So I'm going to sketch a right triangle in the first quadrant where theta is equal to the inverse tangent of x over 1. So that would mean that the tangent of theta equals x over 1. So opposite over adjacent. And using the Pythagorean theorem, I would see that this third side, the hypotenuse, would be square root of 1 plus x squared. Okay, using Pythagorean theorem, let's see how we did that. 1 squared plus x squared equals, we can call that r squared, which is the third side. And r then would equal the square root of 1 squared plus x squared. All right, so now I've got a triangle I can work with. You just draw a triangle. Now the sine of theta would be the opposite over hypotenuse in our sketch. So opposite is x, hypotenuse is square root 1 plus x squared. And there you have it. The sine of the inverse tangent of x is equal to this expression. Okay, hope the video went well. We'll see you in the next one.